The Acrobat button in the bottom. Perfect. And then you can click in it and go Control L.
So if anyone is there in Zoom land, tell me if you can or cannot see this.
Yes, it works.
Fine. Oh, okay. So our next speaker is Sinan Gunturk, and invite him.
Thank you very much, Mel. Thank you very much for organizing this conference and the invitation. So the title is here, Exponential Sums and Conjecture Involving Quantization of Bandlimited Functions. Joint learning. My colleague, Will. So I would like to first point, so Mel, you'll recognize this, right? So this is from ancient times, from 2000, year 2000. There was a DIMAX conference called Unusual Applications of Number Theory, which Mel organized. And then I presented the kind of the very origins of this work there. So this is really, the beginnings is very old, but almost nothing was done for about like 20 years until Max joined again. So this is I also gave a talk about the origin of this 2003. This is 2003. You can see I don't know if you can see it all, but so I gave this talk, well, not this talk, but the origin between talk by Joseph Soimoshi on standard product sets and another talk by Mel on additive number theory and the house of dimension decay back in 2003. The old days. All right. So here's the context. So what's bandlimited? So bandlimited functions are functions which have Fourier transform with bounded support. So they don't have frequencies beyond the maximum. And the classical audio signals, at least as far as we can hear, we don't hear beyond, let's say, 20 kilohertz. And this is, if I were to say sampling, that's what it looks like. And if you were to zoom in that little kind of blue area, zoomed out version, you see it gets smoother, even though not so apparent in the original one. So bandlimited signals, I mean, if you have a finite support, a bounded support in the Fourier transform, you're actually smooth. You're analytic with, in fact, controlled derivatives. So if you really zoom into the signal, you'll see something like this. I'm going to put this up as a model. So the most important thing about bandlimited signals is the sampling theorem, the celebrated sampling theorem, due to Shannon, Nyquist, Whittaker, Kotelnikov. You have another name. So here you see the Fourier transform. It's in the frequency domain, bounded support. If I use a smooth cutoff, so that blue cutoff function is 1 on the band of this function. If I first, well, imagine periodizing this Fourier support in the Fourier transform by an amount lambda, which, well, by the way, I have normalized the bandwidth to be 1, just so you can set the scale. So I'm periodizing by lambda, which is bigger than 1, and using the smooth cutoff, which I can. And then if I expand the Fourier transform as a Fourier series, I notice that the coefficients are just samples of the function at a spacing 1 over lambda. So it's just a simple calculation, which then if you invert this, you find the sampling theorem, which tells you that you can recover the function perfectly from its samples taken at a rate lambda, so lambda samples per unit interval in this case, and then you can recover by an interpolation using this kernel phi, which is a smooth cutoff. So this is the sampling theorem. It's a perfect reconstruction. Now, here's just some basic things about facts about A to D, analog to digital conversion. So the first step is the sampling step. Of course, the next step is you have to digitize, right? And this is called quantization. First, the first that one can think about is just discretize the amplitude, because you can already recover from the samples. Just do this. Except this is not what engineers prefer in practice, because creating a very fine, high resolution kind of quantization is expensive. It requires high precision hardware, whereas sampling actually is cheap. Sampling can be done with very high efficiency, very high. You can oversample. So you can. So what engineers have devised long time ago, more than 50 years ago, is this concept of oversampled coarse quantization, and it can be as coarse as 1 bit per sample. So it's the same signal here. What we're doing is we're sampling faster than we need, and then we're coming up with a rounding procedure, either to the +1 level, let's say, or a -1. Again, the amplitude can be normalized here, but we have to do it in a clever way, and this is kind of telling you that I'm not just taking the sign of the sample, I'm actually doing something more elaborate. And then after this rounding, I just recover from those signs. Okay, so that's the concept of oversampled quantity quantization. And you can again see that as the signal level is high, or where the signal level is high, you have more ones, +1s, and -1s. And when it's low, close to -1, there's more -1 than +1s. So you have to do it just kind of balancing. How to do this is the question, right? You can also pose this problem in the 0-1 world. Nothing is different, everything is the same. You can think of it as the rounding to 0 or 1. Okay, it's the same function. So the problem is, you give me the samples which your hardware is collecting. These are exabands, right? Then you need to give me these quantized bit representation. Those are QNs. In this normalization, there's zeros and ones. So that if I reconstruct from those QNs using the same interpolation formula, then the approximation I get is a good approximation of the original function. And I actually want this to perfectly recover the signal as I oversample more and more. So and the question becomes, how well can we do this? And you might say, can you do this? Yes, you can do it. There's a lot of theory behind this. The most classical method is called sigma delta quantization. So there's a reason for this. It's called sigma delta. So what you do is you take the samples, you start accumulating. You take the partial sum. That's the first step. So that's the sigma step. Okay, and then you round it to either the nearest integer, or you take the floor. That's the quantization. And then you differentiate it. There's a differencing scheme. That's the delta. Okay, so you can actually implement this with a very cheap, simple hardware with a feedback loop that has memory 1. So on 1. So what this equation does is, if you look at the difference between this accumulated sum of the samples and its integer part, of course, this is now the fractional part. But then if you take the difference of this, you'll just take the difference of these. Those are the input minus the output. So you have a simple recurrence relation, un minus 1 for the fractional part, which is the kind of the rounding error that you have. So what this algorithm is doing is, it's actually controlling the accumulated rounding error. So it's doing something, it's already introducing structure in rounding output. It's very basic. And how do you approximate with this method? So if you just look at the error, which I call E sub lambda, all you have to do is, well, we had xn minus qn equal the difference of un, so you plug that in. And then you have to do a summation by parts. I don't need to explain this trick. So delta goes to the other side. And phi being a nice cutoff function, it actually is smooth. All we need at this point is to utilize it being a bounded variation function. So overall, what we get out of this knowledge or this expression is that the error of reconstruction is uniformly bounded by 1 over lambda, up to some constants that depend on phi, but I don't care about that. So as lambda is increased, I can recover the signal at the rate 1 over lambda. So But the engineers, of course, they use these things and they simulate, they implement, in fact, and they've observed faster decay, faster than 1 over lambda. In fact, they observed that if you look at not uniform error, but if you look at the squared error averaged over time, and then take the root mean square error, decays at the rate lambda to the exponent minus 3/2. So you have this extra square root calculation, which should be very familiar. So where does this come from? This conjecture. But, well, I should also say in what sense is this? So there's two formulations. One formulation is a strong formulation. So this is true for every function. If you average over time, the squared error, you get this error decay. And there's a weaker formulation, which is on average, another average, which is over a class of functions. If there's a model of your class, then if you average over those as well, then you get this. So they're different because the constants that you see, of course, can be dependent on the function of interest. So whether you can average constant is not clear. So and in fact, there are known results which shows that this strong sense does not imply the. We have to be careful about this. So this folklore conjecture has been proven rigorously for constant functions. Constants are also band limited, just have 0 bandwidth. Okay, but on average, so if you actually average over the value of the function, so this was first done by information theorist Bob Gray, and also this result was used to support the conjecture. There's also a robust version that I did. Okay, so this is now. It was also stated, but not quite technically proven, for pure sinusoidal signals. So it's not exactly stated as an error bond, but rather as some implicit formula for the quantization noise spectrum. So that's why I'm not quite stating. So there's some evidence for this folklore conjecture, but it's not so clear. Now, in terms of what is known, the closest result that was proven for general band-limited functions is in the pointwise sense. So if you pick a point in time and then go through this algorithm and look at how the error actually goes to 0, well, it's at least 1 over lambda. We know that's uniform norm, but it actually goes faster. The exponent, you can save about a third. Okay, so lambda to the minus 4/3 is what you can show, except the constant depends on the value of the derivative of the function. It should be non-zero, which is generically true. And if the value is close to 0, then things start kind of getting bad. So you can't actually integrate this. You can't, the dependence on the constant is implicit and it doesn't quite average over time. So this is the point why that's strictly point. Now, on the other hand, if you look at strictly constant functions, again, like a very basic case, the uniform norm actually decays at the rate almost lambda to the minus 2. So you can save the full power here. So this holds for almost every x. It relies on Kinchin's theorem. So it already tells you that constant functions they don't actually, they're ruled out for that strong formulation because you actually have better decay. Okay. Now, okay, as I said earlier, this was the state of like what was known almost 20 years ago, and all of these results were put into the museum because much better, much more elaborate algorithms were devised. So in fact, you can come up with other more elaborate algorithms for which the error decays much faster. So initially it was exponential with a log square, so lambda to the minus log lambda. And then Sergei Konyagin did something for constants with the square root of lambda in the exponential. Then I proved that you can actually have full exponential decay. And up to the value of this constant, which we improved in joint work with Percy Dayton and Felix Kramer later on, we don't know what's the best constant, but exponential is the best one for in general. So why bother about this first order method, which I'm very coordinate? Well, it's still a classic. It's one of the first, in fact, it's the first algorithm that was devised, and it's still useful in some kind of limited hardware situations, and it's poorly understood. So looking back at this, so Max got interested in the problem and told me, look, I don't believe this conjecture is true. I said, what do you mean? And then he said, look, if you kind of look at this type of function, it should be false. And then we kind of worked it out. Yeah, which tells that you can actually, in this root mean square sense, you can the Volkow conjecture is false in the strong formulation, meaning there are functions for which this square time average converges. This is, by the way, the best coverage norm, and it's at least lambda to minus 1 plus. So it also, so this proves the strong formulation, but also it gives us the first type of lower bound for the supremum norm of the same type, which was not known before either. So it tells you that the crude bound is from sometimes sharp. I know that I should be stopped, right? But what I will say is that, well, if I may,
Yeah, a few more minutes, sir.
oh, do I have? Oh, okay, sorry. I was. So yes, so we have this lower bound, which disproves the conjecture, and it's not just an existence. Okay, the proof actually is constructive, and the functions can be explicitly stated. But actually, the proof does not suggest yet if the weaker average formulation should still be expected to hold. Okay, so if you average over a signal class, maybe it's still true because the engineers did these simulations, extensive simulations, they find it. So it's not like I can dispute that. It must be true in some sense, but they are not always clear about what they do. And also, these are extremal functions in some sense. So if there's an average in process, they may not be. So where's the number theory? Maybe I should just say a few things about the number theoretical context. So this is, again, first order sigma delta algorithm. What it was doing was it was accumulating the samples, taking the integer part, that's Qn, and then their difference is Un, which is just a fraction part of this accumulated samples. Well, you can, once you write this, you realize that this is nothing but it's a rotation on the circle where at each time instance you rotate by the sample value. So it's a slowly varying rotation. Of course, if the rotation is constant, and if it's, let's say, irrational, then you get equidistribution. But here, well, constants are a very special case. So what does really happen if your function is not constant, but as you oversample, it's really slowly varying. So you can expect a lot of tools from now. These were used actually the original. So the old kind of improved exponent follows exactly by quantifying the equidistribution of this and one has to come up with a local discrepant bound. And why is it used? So, well, there's another expression for the error where after summation by parts, you're left with UN. And then this is the difference of that, the averaging kernel. But this sums up to 0, so you can stick in a constant, which is the mean value of UN. Okay, so once you see that, this is, you can say, okay, I can do another summation by parts and completely eliminate the influence of that averaging process. So you're left with dealing with kind of how well does this UN, which is found by rotating on the circle by example, average out over time. So there's classic inequality of Cox-Mann average Turan, which connects estimation of these quantity into exponential sums. Many of you should be familiar with this. So here in the exponential sum, the phase is the cumulative sum of the sample. So what goes into the method is an observation where you can actually.
The coalition of the Weeding, I'd like to thank you for your constant, steadfast support. It's under your chairmanship that we signed a memorandum regarding the participation of contingents that will be placed in Ukraine, and it's the coalition of willing that seeks to guarantee the security and stability after this war, and there were also resolute steps taken in order.
I thought I was being reminded to stop, but I just okay. So there are many experts here about function sums, and you know that there are many tools. So the phase here is actually it's you're accumulating the sum, but actually it can be realized as the sampling of another bandlimited function. Okay, so this is once this is established, then you can use standard tools as truncated Poisson sum and the stationary non-stationary method combined with like the corpus line aspect. So these are kind of already what the tools that were utilized previously, but the new result also uses many of them. Now I won't be able to go into what else we do here, but I'll just say that if you're interested, the preprint is coming. So that's why I'll stop. Thank you.
Any questions for us? If not, we thank you for your talk. And then we Kevin, can you deal with this?
Don't install Ubuntu.
No, I'm not. So there you have your talk on a USB on computer. Okay, it's possible. I don't know how to make it possible.
I didn't hear. You've got it on a
the
USB?
USB both.
Okay, USB move over is easiest.
Sinan had-
If he's afraid to just pull.
Not right. I haven't seen it today. Unusual applications. It's 20 plus years. I know it's sitting on a shelf of my cellar.
It'll show up down here as soon as it gets working on this.
And how they came about. With Ron Fields, I hear. Yes.
Yep, we gotta get that's not visible first. You want this to go full screen? Yes, yeah, so share. Okay, so.
You know that, Steve, did you need things erased or?
What were you at this full
But you know that has to
really
be
do something
No,
else.
it is not.
This is ignorant New Yorkers. Why is this hat illegal?
The B on it. My wife just bought this and she says there is a rivalry.
Okay, so the way you phrase
Is
it,
that a baseball?
it is Williamstown and Cal Ripken. It's for Berkshire, it's the local online newspaper. It's not a Red Sox hat. So you are the only person who's ever said because it has a B on it. Everybody else says it's a Red Sox hat. So I will take it off because you said it has to be.
No.
I know, we
It's okay.
play everything
It's
is
okay.
safe, everything is safe. I do not have anything to be on that. You're late.
I just always have to remember that that's the day when you hit it with a stick instead of kicking it.
I already have some base that.
And now this should move you forward and back.
So, Kevin, is it shared?
It is shared, it is recording.
Oh, very good.
Fingers
Our next
crossed. It's all
speaker,
good.
Ilya Skredov from Purdue.
Thank you for the invitation. So I want to start with maybe an old question which was maybe forgotten. So it was formulated by Korolov years ago. So we have a prime number or a general composite number, and let D be the dimension of our problem. So the question is it possible to find a tuple of coefficients, so-called optimal coefficients, just residual modulo P, such that for any non-zero x, the following product is large. This is P to the D over M. M is a parameter. The parameter that measures the quality of our tuple. So the absolute value is just the ordinary absolute value in FP. And this question is kind of widely open. It's easy to see that it's not possible to take M greater, less than 1. It's just Dirichlet principle. And what is known is this classic bound of Korolov that you can always find A1, AD such that this inequality takes place with M of the form log to the D of. So that's the question, that's the open question. And today I will say just there are just few known things about this question, and maybe I will concentrate my talk on the simplest case, T equal to 1. Okay, so that's just reformulation. And if D is greater than 1, then you can think about this question as a discrete version of a famous Littlewood conjecture from the finite approximations. So in Littlewood conjecture, we have D real numbers, and we want to show that actually these lim-inf, if I consider n times fractional part of alpha 1 n and so on, alpha dn is 0. So it's not possible to construct a tuple of real numbers that correlate with others. So this is widely open question. It's kind of the central question, probably in the Fontane approximation. What is known? This is a famous paper of Islander, Katov, and Linda Strauss that says that actually the set of exceptions in Littlewood conjecture has 0 measure in very strong sense. It's actually has it's easy to see that the Lebesgue measure of such exceptions is 0, but actually this set has Hausdorff measure 0. And so maybe I should say from the very beginning that the collection of such optimal coefficients consists of very atypical tuples. So if you want to construct these optimal coefficients, then you must work with measure 0. So this is kind of expected. And this bound of Korobov is just a typical choice of A1.
Unfortunately, I'm a professor and I can adjust my schedule to be.
All right. So this is a result of Sinan Gunturk. So in discrete setting, it's possible to show the same relatively easy because this is a very deep result, and the discrete version also requires some rather deep tools, but it's all right. So yeah. So once again, the measure of these optimal coefficients is 0. All right, so what about motivation of Korobov and others? So a piece of history, it was an interesting seminar at Moscow State University in the 50s that collected not just number theorists as Korobov and his students, but also some people from applied mathematics as Bakhalov and Chiltsov, and probably this kind of so-called questions arise in these seminars. So their motivations were rather practical. They wanted to integrate functions. So we have a function in d+1 dimension, so say 2-dimensional function. And we want to approximate the integral our function via a finite number of points. So we choose a finite set x, and then the integral can be approximated by this finite sum with this arrow. This is a famous classic theorem of Cox-Maglavka. So the variation of f depends on the f only. And also we have another term here, the discrepancy of x. This is just a measure of uniform distribution of our sequence x. So we take any rectangle, we compute the density of my sequence x in this rectangle, and we subtract the expectation, and we take the maximum. So the real question now, how can I construct the sequence x with the least discrepancy? That's the question. So, and we will see that optimal coefficients help a lot here. So, but from the very beginning, I want to say that there are some beautiful lower bounds for the discrepancy. So you cannot construct a segment x which is too uniformly distributed, if it's possible to say so. So, for example, in dimension 2, so it's a classic theorem of Schmidt that the discrepancy is at least log x over x. And moreover, in higher dimensions, we have some non-trivial bounds that belong to Bilik-Resi and Parashanian. All right. So that was motivation. Yes, so that was a theorem of Cox-Maglavka. And so what about optimal coefficient? So to construct that x, you can use random methods that work awfully actually. So Korobov, Zaremba, and others, they suggested to consider the following constructive winding, a very simple collection of points x that depends on these numbers a1, ad. So this is just a winding of d+1 dimensional torus, right? The tangent depends on this a1, ad, and then it's relatively easy to show that if you are able to find this a1, ad such that this product is greater than p to the d over m, then the discrepancy is basically m here. So yeah. So yeah. So you see, if the constant m is a really constant, then your discrepancy is kind of probably missed a lock here. Sorry. Yeah, I missed a lock here. That's it. All right, but let me show you what is known in the simplest case of D1. So in D equals 1, our problem looks very simple. So we want to find just one number A, such that x times X is greater than P over M. And in this case, the winding is very simple, just two-dimensional winding. So it turns out that actually this question is equivalent to find A such that all partial quotients of A over Q are bounded basically by the same constant M. So this is a result of Zaremba and Korobov. So if you consider your two-dimensional winding, then actually the discrepancy can be computed rather precisely in terms of the continued function of expansion of A over Q. And this is basically the C. Right, so the discrepancy is bounded by that. And you see if M very constant, then the upper bound for discrepancy is log Q over Q. And here we have the same lower bound thanks to Schmidt's theory. So it means that if I can construct, if I can find A such that all partial quotients are bounded, then actually I'm able to construct an optimal collection of points. So that was motivation of Korobov. Yes. All right, so now I'm going to talk just about the case D is equal to 1. Are there any questions?
Use some notation for absolute value.
Sorry?
There's like a notation earlier that absolute value by field element.
Yeah.
You mind just clarifying exactly what that?
Yeah. So. Yeah, so this is just, this is 2. I mean, yeah, it should be from 0 to I meant that I consider FP as the collection of points between P minus 1 and minus P. Yeah. All right, other questions? So so now we have this this precise question, which was just formulated by Zaremba. So we have the continued fraction expansion. We have a denominator Q. So for Korobov it was a prime number, and we want to find A such that the numerator A such that all partial quotients C1, C2, and so on are bounded. And Zaremba asked about a precise constant M here, 5, 5 because of some small exceptions. So later we'll see that probably even a stronger result takes place. Hensley conjectured that for sufficiently large Q, even the constant 2 is enough. Right, so, and he formulated a stronger hypothesis. So he, first of all, he considered the real analog of these sets of Zaremba's numbers, of Zaremba's numerators. So suppose that we have a collection of reals such that all partial quotients of them are bounded by M. It's known to be a set of measure 0, but you can compute the Hausdorff dimension of this set. There is a nice formula of Hensley. Basically, it says that the dimension is 1 minus 1 over M, equal 1 over M. And it is an important fact for us that W2, so the Hausdorff dimension of reals such that all partial quotients are bounded by 2, this Hausdorff dimension is strictly greater than 1/2. So using some heuristic on uniform distribution, so Hensley conjectured the following lower bound for the set of ZM of Q. So ZM of Q, what is ZM of Q? So in the Rambus conjecture, we want to find just one H such that all partial quotients are bounded by M. So now consider the whole collection of this numerator A such that all Sj are bounded by M. So by some heuristic of Hensley, I can say a few words about it if you want later. So the size of ZM of Q must be Q to the 2Wm minus 1. And you see if the Hausdorff dimension is strictly greater than 1/2, then this quantity tends to infinity, and probably the constant M is 2, just 2. All right. So another motivation. So later people realized that actually, if you want to compute the discrepancies of some classic sets like this or that and that, it's more convenient to count not just the maximal partial quotient, but the average of your partial quotients, and they introduce this average value of partial quotients, and one can show that actually for these sequences or for this simplest expander, AX goes to AX, so the discrepancy of such things are all controlled by the average partial quotient. And there is another of the Rambus conjecture, a weaker version of the Rambus conjecture, that the average value of partial quotient is bounded by a constant M. It's conjecture form. All right, so what is known? So the first result about the Rambus conjecture was obtained by Korobov, who showed that actually M can be chosen to be log P, and this is exactly just a particular case of his general bound for M here. By the way, later I will formulate the precise relation between continued fraction and this inequality. All right, so also you can study the distribution of this maximum, right? You can even prove some central limit theorems for this maximum. But so the point is that typically this maximum behaves like a log of Q. So that is why I said that Korobov's bound can be obtained just taking the typical vector, the typical HQ. All right, so for some particular Q of the form 2 to the M, 3 to the M, it's possible to prove the Rambus conjecture using so-called the folding lemma. You can just constructively you can just give some constructions of these A's with bounded partial quotients. Right, and so as for the average, it was a beautiful theorem of Larker, who showed that actually for the average you can improve this log of Korobov taking double log. So this is again an average argument actually, but you kind of consider average over the average. So in a way, this A is also typical, but it's typical in another way. All right, so yes, and also so the Rambus conjecture is related with some questions from pure combinatorics. So it was realized rather recently by Park, Chan, and his and their co-authors that if you want to compute some specific combinatorial configurations, then the Rambus type result usually help. Also, it's related to so-called Macmillan conjecture about arithmetic chaos, and so on and so forth. All right, so what about the rather recent progress on the Rambus conjecture? There is a beautiful theorem of Burgan and Kondorovich who proved the Rambus conjecture for almost all denominators. So more precisely, if I consider first n integers, then for all q outside this small set, the Rambus conjecture takes place with the constant, say, m is equal to 50. Yes, so you can say that the density of sets for which the Rambus conjecture takes place is 1. So after that, this question was considered by elementary and non-elementary methods. And now probably the best result in that direction belongs to Yurikhan, who showed that you can even take m is equal to 4 if you care about all but small denominators. All right, so, but again, this is a little bit another story. In Korobov's formulation, we have a suitable denominator, and we want to construct A, or we want to find, or we want to prove the existence of A. We don't want to say anything about almost all denominators. So also, we proved two so-called epsilon approximations to the Rambus conjecture. So epsilon approximation means if epsilon goes 0, then you obtain the Rambus conjecture. So we proved that for a prime P, it's possible to find A such that all Sj are bounded by M outside this middle interval, epsilon interval. Right, so this middle interval is kind of the gist of the story. Actually, it will appear several times during this talk. Yes. So you see, if epsilon is 0, then we have the Rambus conjecture. And another approximation, epsilon approximation, so-called modular version of the Rambus conjecture, comes from Hensley. So now we have two numbers, P and Q, and they're kind of comparable to each other. So Q is, first of all, is divisible by P, and Q is controllable by P in the sense that Q is P to the 1 plus X. So then for this Q and P, so for a given P, you can find such a Q such that all partial quotients are bounded by M. And again, if epsilon goes 0, then you obtain the Rambus conjecture. All right, so recent results. So now paper with Mashidin and Murphy, we considered the following improvement. We proved the following result, the following improvement of Korobov's theorem. So we improved this Korobov's log by a log of Q. Yes. So under the following conditions, so we considered the collection of denominators. It looks rather strange because the proof is kind of inhomogeneous. we consider the collection of denominators, first of all. So if we have all primes in the expansion of Q to be sufficiently large, sufficiently large means that P is greater than an absolute constant. So the second case, so you can consider any square free number, sufficiently large square free numbers, say prime numbers. As the third case, you can consider these denominators of the form P to the n. So now P is any prime, but n must be sufficiently large. So for these denominators D, as D includes all square free numbers, the density of D is positive, say. So for all these D, you can improve Corbel found by log Q. So this is actually a rather deep result. It requires a lot of technique just to improve, to have this improved. So we will discuss it later. So what about new results? So first of all, so now my Q belongs to this set D. This we'll discuss it later, right? And we consider first of all an improvement of Larkin result. So if you take m is square root of log Q, then it's possible to find so many numerators A such that the average of partial portions is bounded by square root of log Q. So we kind of took the square root of Larkin's log. And you see here this Q to the W m minus 1 is precisely Hensley's prediction, even times by some growing factor. All right. So the second result, it's actually a byproduct of the previous one. We consider this m roughly square root of log Q, and then again it's possible to construct so many A's Q to the 2Wm minus 1. Again, this Hensley's prediction such that all partial portions of A or Q are bounded not by m, but m plus 2. There's a small flow here. It's not important because m tends to infinity, right? And also we will see that I don't know why people didn't realize it, that there is a natural threshold here, square root of log Q. And you see that the behavior when m is larger than square root of log Q and lower, they're completely different. Yeah, so we will discuss this threshold later. So, and finally, now I know how to formulate it with the result in a simple form. Yeah, so finally, so there is an absolute constant m such that we have so many yes. So we have so many numerators A and such that all partial portions again bounded not by m but 100. It's a flow. So of course, if m is constant, that 100 times m is also constant. But in the terms of Hausdorff dimension, it's another exponent, right? You see that W m is 1 minus 1 over m. If you divide it by 1 over m over 100, it's another exponent. Right? So unfortunately, the number of such A's have a similar form, but it's not precisely Hensley prediction. Because we use another method. All right, so are there any questions so far? Again, I do care about the number of such cases. For example, in Macmillan's conjecture, you need to count it. All right, so the ideas of the proofs of the previous results, and at the very end, I will say about the new technique. So first of all, concerning this, well, let me recall. So concerning this inequality and the continued fractional expansion, right? So previously we formulated Korbel's conjectures in terms of this product, and now we are talking about continued fractions. So the relation is very simple. So these two things are equivalent. So we consider this linear equation Ax is equal to y, the simplest equation ever. And then it's possible to show that if the solutions of to this equation lie under the hyperbola xy is equal to q over m, then all partial quotients are bounded by m, and vice versa. If you know that all partial quotients are bounded by m, then all solutions lie above this hyperbola. So this equation has a natural symmetry. You can multiply by A inverse, say if your Q is a prime number. So you obtain this similar linear equation, the similar hyperbola. So this symmetry is kind of natural. So in classical terms, you can say that if you consider A inverse over Q, then the expansion of A inverse over Q is basically just a reflection of your initial expansion. So it gives us the way how to construct these Arambos numerators. Very simple. Consider just numbers with the first half, the first half of partial quotients abounded by m. So I said, I don't know, x. And if you are able to find an element such that A such that A inverse lives in this set x, then the second part of your partial quotient is bounded. And hence, your question is the following: you need to intersect x and x inverse. Right. So that is the way of thinking. So this set x is called ZM of t. It's so we take a parameter which is less than square root of q. Square root this 1/2 here responds to the fact that you take the first half of your partial quotients, and moreover you need to take a little bit less than 1/2 minus epsilon. So and you consider so all A such that not all Sj are bounded by m, but 1/2 minus epsilon of Sj are bounded by m. So this is a kind of our Zaremba set, and we want to intersect Zm and Zm inverse. If we are able to do this, then we can say that okay, the first half of my elements is bounded, not the first half precisely, but 1/2 minus epsilon, and another 1/2 minus epsilon elements as J are bounded. Right, and still we will have this middle interval. This is the main difficulty. All right. So what is known about this set ZM of T? This is a classic set. Actually, it's a collection of intervals. They are obtained by it's a counter type set. You can compute everything in it. You can compute the cardinality, how many intervals you have. Moreover, you can even prove that this is alpha Naive set, so it indeed has some counter structure. So everything is known about ZM of T is collection of interval, but if you consider ZM inverse, then your interval becomes not an interval. So you assume that ZM inverse is a random set, and it gives you hope that the intersection must be kind of a random intersection. So, and formally, we need the following main growth lemma. We need to solve the following innocently looking equation. A plus C, B plus C is equal to 1. So basically, we want to find the inverse element here. So the context here is the following. So A and B are huge sets of size e to the 1 minus epsilon. And if the length of my interval, I mean, my counter set is a collection of intervals, so it's a very short interval n. And then the number of the solution to this equation is the expectation minus and the error term. So previously, people considered this equation as a equation about inverse elements for IK, and they used analytic tools like Klosterman sums. But in our regime, n is e to the epsilon and even log, so this is absolutely useless, right? So, the main idea is to look at this equation as an action of SL2 or GL2. So you can rewrite this equation in this form, and this is a temporary problem now. A and B are sets in FP, huge sets in FP, and this guy is just a collection of matrices from SL2. All right. So the relation between continued fraction and SL2 is a classic thing. So let me just show you this formula, right? If you multiply these things, then you obtain the denominators and numerators of the continued fraction expansions. So more concretely, we, as I said to you, we rewrote this equation in that form. G belongs to a concrete family of matrices. Okay, the determinant of -1, not important. Right. If you want to solve this equation, as always, you need to compute the exponential sums over your set of matrices. In these non-commutative terms, it means that you need to compute representations of your matrices. To prove that the exponential sums over this collection of matrices is small, it's equivalent to study the growth. This is equivalent. Right. So the question is, what can be said about the growth of this family of matrices? And for growth, we have beautiful results of Helmholtz and others. So Helmholtz result is kind of a driving one here. So we know that if you have an abstract, an average set that generates SL2 of FP, then actually generates SL2 of FP very quickly. The product of A times A times A is large, or it coincides with SL2. And you can reformulate this combinatorial result of Helmholtz in analytical terms that was done by Burgan and Gambur, who show that actually with the help of Helmholtz theorem plus a little bit of representation theory, simple representation theory, you can actually compute the number of solutions to any linear equation in SO2. So after that, people generalize it to affine sieve, to p to the n, to other things, and finally, so we have this result because of this result has three parts because of these generalizations of Helmholtz result that were done for square of three primes, for q's of that, for and for p to the n. And that is why we have this theorem in such a case. So recently I was informed that actually there is a general theory for crossing SO2 of P. So this main theorem, main lemma, takes place for any Q, and you can think about the set of T's just the set of O. All right, so 10 more minutes. Okay, suppose that we have this growth result, this main lemma. How can we proceed? Very simple. So we have our parameter t. This is just it indicates that we consider 1/2 minus epsilon partial portions. We have our quantum type set Zm. It's basically I plus Cs. So this is just a collection of shifts of one interval. It's invariant under this addition by I, right? And hence, having this equation in two variables, you can increase the number of variables to 3 or to 4. It's not really important. And now we arrive to this equation here. And you see that for this equation, it's possible to apply the main lemma. Yes. And you see that there are many solutions to this equation, namely the random intersection, the expectation, and the error term. And it gives us a relation between parameters epsilon and m. So we have proved the following. So if our simple linear equation has a solution, then the solution to this equation must be what? It must be larger than t, but by symmetry, it must be less than q over t, basically.
All right, just let me know what I have to do.
When you find that not like technical staff that can arrange for it to be live.
Yes.
No, I know. No, we're very popular. Did you have to do it yourself? Or did you have to do it?
We had to contract